So what I was kind of thinking to talk about was to show some benchmarking results, comparing performance, data read performance of the same file, but in the original and cloud optimized form, when both of those versions of the file were either in a local file system or in S3 in Amazon. And again, it's a single file, so I'm not pretending to explain everything for every use cases. And we all know very well, HDF users tend to be very creative how they want to, what type of data they want to stuff into their HDF5 files. So that's why I'm very cautious to say big conclusions, but it's, I think we'll get to some conclusions. And I think that'll be enough for today's session. So the file that I'm talking about, it belongs to a NASA instrument. And I had this session, I don't know, I would say maybe even a year ago or something like that, where I talked more about the instrument and everything else. I don't want to spend time on that. But anyway, the file that I'm now going to talk about is one file from this JEDI instrument. This product is called Level 2B. Level 2B as a number, and stores data, as you see here. It's a canopy cover and vertical profile metrics data, global footprint level. And this image actually is very useful because, although I don't want to talk about this instrument, these lines that you see that sort of go diagonally across is depiction of the laser beams that are shooting from this instrument down to Earth. And these are essentially their footprints, their trajectories across a real image of summer on our planet. If I zoom in a little bit more here, I don't know if it's clear enough, but you can see essentially these little circles. That's one single laser impulse. Laser pulse. That's how this instrument operates. By the way, this instrument is mounted on the International Space Station, so it's not really a satellite instrument, because the space station is much lower in altitude than a normal polar orbiting satellite. But, you know, it's good enough. And so I'm using one file about that. And let me share something else. So what's in this file? That's what I'm thinking. So I'll show you now. Again, I'm trying to quickly jump through a bunch of stuff. So let's share this on the screen. So what's in the file? We can run a lot of things, but I'm using the h5 stat command from the HDF5 library tools. And the contents of the file, as you can see, there are 43 groups. There are just over almost 1,600 HDF5 data sets. And probably what would be also interesting to know is we have 120 data sets that are contiguous. The rest are chunked. And all of them are chunked with gzip or deflate or zlib compression method, which is very, very common because you find this zlib compression library everywhere on almost all the computers. And again, I'm trying to jump over the whole talk about cloud optimized HDF5 file, what it means. I also had a presentation on that, one of these sessions. But for us here, specifically means that we divide file in pages, and these pages hold of certain size, and these pages hold distinctively different type of data in them. One is internal file metadata, and the other one is the actual data. When I say the actual data, you may ask me, what is that? Well, I would say those are data from contiguous and chunked data. And anything else is essentially internal file metadata, I think. And so in this particular case, we are using a file page of 8 MB for this file, but I'll talk a bit more later about the choices for the benchmarks. So this is an 8 MB file page, and here on this line, the HDF stat says the entirety of internal file metadata is about 5.25, 24 megabytes. So what that tells me is that the entire file metadata fits into a single file page. And that's what makes this file cloud optimized. If that was not the case, if we haven't used this paged file approach, all these 5.24 megabytes of internal file metadata would be shotgunned, dispersed across this file in tiny, tiny packets of, I think, 4 kilobytes or something like that. And that would completely destroy the performance when reading data from this file, if it's in S3. So that's the cloud optimization technique applied to this file. And this is the cloud optimization technique that is going to be used for all the files in this benchmark. The other cloud optimization technique is actually making chunks much bigger. And that I not have done that because the best way to do it is when the files are created. But now when you actually have the file with small chunks, doing them for all of them, it's kind of tedious work. And HDF5 tool set doesn't have anything really, really useful for that. So really, the best moment to produce large data set chunks is when the file is going to be created. So in this case, what I'm using is the original file, and all the internal file metadata is collected into a single or couple of file pages. And now here we can see what kind of situation we have with data sets, a bit more specific data set statistics. I talked about this script, about this data, the last time I had session, which was like, I think was September. So I'm not going to go through this, obviously. The only thing I want to mention here, a couple of things, that all the contiguous data sets and all the chunk data sets fit into file pages. So their size is such that they can all fit, which is obviously what you want to achieve. Other than that, I'll just skip it because I talked at length in September. So on to the benchmarks. Any questions so far? Obviously, people can ask anything they want. They're going to be quiet till the end. But if no questions, I proceed. So what did I do in this benchmark? So I got this file and I got a Jupyter notebook that was developed to showcase this type of product, that this file belongs to this JEDI level 2B. And the Jupyter notebook contained a number of data read tasks, let's call them like that, which I call benchmarks here. The overall point of that notebook was to visualize data from this file. So you could say that those tasks or my benchmarks, because I just copied and used them, are kind of biased toward reading basically everything, the entire content of certain specific HDF5 datasets in this file. But I didn't have any other example to use, so I used what I had. And for the files that I wanted to study, as I said, I had the original file as it was produced and archived right now at NASA, for example. And then I produced a cloud optimized version. And when you see this here, let me see. Okay. The examples, the original will have this like a shortcut, but then anyway, I'll continue talking. I'll explain later. It's better. So I cloud optimized them. I just explained how I cloud optimized them. I collated their internal file metadata, and all the other data was in these file pages. And then I put both versions of these files into a local file system, and then I put them in S3. And then I measured running all these benchmarks, accessing all these versions of the files in these two locations, local file system and S3. And I did two versions of cloud optimized files. One was 8 MB by file page. The other one was 16 MB by file page. And at the end, I also said to the library, behave normally or behave in a certain way that's beneficial to cloud optimization. And I also compared all these things together. So, and when I was comparing these example cases, I ran them 10 times in the random order. So I didn't want to essentially run them one after another, or I didn't want to run them only once. I actually ran them 10 times, and they were all randomized whenever they were invoked. And I measured specifically each benchmark for each case, for each run. And then I used the results. So for this particular data, as I said, I'm going to use L2B file, although I had two other product files. There was a level 1B and level 2A, but we're just going to use it. So I ran all this code, so I'm not going to complicate these explanations. Obviously, here's the big picture, and hopefully, so how to read the results. If you look down here, you can see all these use cases. So CO means cloud optimized version. 16 MB means 16 MB by file page. Local means this file was in a local file system. The same file could have been in S3, so you can see S3 here in the label. And if you see PB, that means that I used a specific cache in the HDF5 library that's only available to this type of files that are paged aggregated. If there is no PB, then it means I didn't use it. So in other words, with PB, the library has this extra cache and makes requests per file page. If there's no PB in this label, essentially the library behaves like a normal, conventional, typical library. And I wanted to compare all these results. And what you see here is open. That means that's the name of a benchmark. In this particular case, the open benchmark means it's just an opening a file. So whatever time it was required just to open the file. Whether or not this file was in a local file system, cloud optimized, not cloud optimized, all the other things. So this is a benchmark open, and there is another one called read one, which again, my names are not so intuitive and helpful, but there was some kind of a read, as I said, read task. And the read two means another read task, but obviously not the same as read one, and so forth and so forth. Because I ran them 10 times in a random order, I could actually generate this whisker box plot for each of these cases, for each benchmark. And now we're coming back to the let me come back to this big view and see. You can now see all of them and how much time it took to run them. The y-axis, the time axis here is logarithm. So between these bigger lines, there's a 10 times increase in time. And since I was talking about open a lot, we can now zoom in and see, well, how much time was open taking. And as you can see, this was, very fast, obviously. And then there were some outliers like these dots here and here and here. And that's what was measured. Interesting that there were local outliers as well, which is probably caching on the first one, probably, or something. So that's the big picture of all these tests. Going forward, there was a lot of these plots. I'm not going to bother with this. There's too much detail. But here is the sort of the one big decision I had to make, and that was which statistics to use for this kind of average performance. And obviously there was an average or mean, or there was median. And I chose median mostly because I felt, since I'm also including cases with S3, which knows to have a much bigger spread in terms of performance, I thought that median is probably a better estimate of all the results than mean. Although again, to be completely scientific, I would probably have to do some statistical tests to see which one is more appropriate, or are they the same or similar, comparable. So here is the sort of the big important result, which means after all these runs, after all these benchmarks, and for all the cases of these files, how much time did it take? And this is the plot. As you can see, the original file in S3 took the longest time. We're talking, the median value was 205 seconds to run all these benchmarks. And as I said, I talked about it before when I talked about this metadata, internal metadata that have been in small pieces of 4 kilobytes spread out the file. That's the main reason. And so the one big conclusion overall that we can now very confidently say is that the HDF5 files that were created conventionally are not going to perform well in the cloud. So just moving your file that was for years so well, so useful on your local file system and just plopping it into some kind of object store, it's not going to work. So that's the big result here. The other results are kind of much better, so that's good. But because I said, this result is so much affected by one benchmark that I knew is essentially not favorable to the original file in S3, said let's eliminate that one and see how the other benchmarks for all the other files are actually performing. And this one is actually very interesting because now when the really bad case that we know is not going to be good for the original file in S3, now all the results look much more interesting. First of all, we can see the little, the subtle differences between other cases. But now the original file in S3 is essentially not bad at all compared to cloud optimized files in S3. But when the library is performing again in the regime of conventional typical behavior. So in other words, again, conclusion, if your file is even cloud optimized, but you just don't turn on this special page buffer cache in the library, which then instructs the library to read data per file pages, then basically you kind of didn't do a lot to really improve your performance. Obviously, if all of the benchmarks are being considered, then obviously this is the difference that, yes, there is a difference. However, still, not enough. And so looking at these examples, also we can see that the cloud optimized file with page buffer cache enabled are definitely better in performance. So in other words, using page buffer cache is really recommended for cloud optimized files. So that's another useful conclusion. And the last one that I'm willing to make, and for this I'll try to zoom in a bit better to see. Maybe this one is the right one. So let's see. So here, when you look at it, the difference between cloud optimized file locally and non-cloud original file locally is kind of there. So the other significant conclusion is that cloud optimized files, when accessed in a local file system, are really basically behaving very closely like the original file. So in other words, you're not losing performance if you choose to cloud optimize HDF5 file from the get-go, even if you may not be quite sure that that file will ever end up in an object store. It seems like it's actually better to produce files from the get-go that's cloud optimized than to just produce typical file and then have to do something later to that file if you are migrating to the cloud or something like that. Again, as I said, a single file, a number of benchmarks that I had to work on. So, but I think that this is a very good result. And then what else I was looking at, because when I was running the benchmarks, I actually enabled the logging of the library when it was reading data from the S3. Because the library is using read-only S3 driver, and that driver can generate log information or can log its activities. And so I collected those logs and then included them with these results. So what I'm showing here basically is how many HTTP requests, which are data read operations, were issued by the driver for different benchmarks and different cases of the file. Obviously, now I'm only looking to the files that were in S3 because local file system, they don't have HTTP requests. So, so here it is what I was telling, the reason why the original file in S3 is so bad. So to just perform that one benchmark that I said is really known to be really bad for typical files, the library had to make 9,145 HTTP requests. Which is a lot, and they all come sequentially one after another. So that's the reason why. And now we see other cases where obviously that number is never reached, but there are interesting things. So for example, for this read 3 benchmark, the original file needed 311 operations. For the cloud optimized file with 8 MB file page with page buffer cache, the same thing needed 29 HTTP requests. And, here we go for different cases. And that's also one of those useful data. The other one that I said, okay, these are the HTTP requests, but how much data was actually brought in from that file for these HTTP requests? Because the number of requests is one thing, how much data each of those requests requested is another. And so I did this comparison as well. I simply summed up all the bytes that were requested per benchmark and all that. And as you can see, there's interesting cases. In this read 3 operation for cloud optimized file, with 16 MB page, with page buffer enabled, it was 95% of the file was actually read. It's almost like, another 5% and you would download the file, in other words. So that was also an interesting result, which I didn't expect. But now, why? Well, first of all, 16 MB file page is a lot. And so since the library with the page buffer cache enabled is reading in file pages, now you're basically reading 16 MB regardless of how much data you need. And so these pages are now coming and they're all 16 megabyte, and that's why basically we strictly speaking, we almost downloaded the file in this particular benchmark. Whereas compared to other one, the same file with only 8 megabyte file page was 76%. So almost 20% less, just because the file page was now 8 megabyte. However, the original file, the one that makes so many requests for things, however, in this case, it only was 9% of the data of the file size was in this request. Because on the other hand, this library just asks now the data that really, really needs. And those are these little things or chunks or contiguous data sets. And that's how much it came out. So those are the interesting results. But still, don't forget, even with all this 95% of downloading the file, overall, when looked over across all the benchmarks, this case was much faster than the original file. So, that's how it is. And then later I started plotting these things where I'm doing number of requests and total retrieval of file content. Obviously, what you want, if you look like this, you want to be in this bottom left corner. So not many requests, not too much data. But this is only those two things. When I actually now plot the time it took to run everything and the amount of data brought in, or the number of HTTP requests and the time, you obviously see that you really ought to be here. Small requests and small time. And now we can see which one of those. So there is some kind of clustering here, but I haven't really. Well, maybe I looked at and I had some conclusions, but I forgot them. So, yeah, anyway. So that's that. Any questions?
Yeah, I guess I have a basic question. So you were just mounting this your S3 bucket as a disk, were you? I mean, you're not using HSDS or anything. Are there advantages in using HSDS instead of what you're doing here, or am I misunderstanding what you?
So yeah, okay. So yes, so there are now two ways how you can go after some HDF5 data in the cloud. The one that I was talking about is using the HDF5 library and its read-only S3 driver that goes directly to S3, makes HTTP requests to S3 using S3 API. So that's what I was talking here. The HSDS would be a different pathway. You would go from the library through its REST virtual object layer. That layer then goes to the HSDS instance, and then HSDS instance talks to S3 at the backend. Why I chose this, I was really interested in the bare metal performance. So in other words, HSDS is the middleware. And you'll definitely have a further slowdown in performance because then the HSDS has to do its own thing before sending you some bytes. What is the difference here? Well, if you're in the cloud, in other words, there are no costs for your data getting out of the cloud. And if you are also set up everything in the cloud the right way, so there are no additional costs for data getting out of S3 to your cloud EC2 instance or some other compute resource, then basically HSDS cannot bring savings to you. Because if you're however, if you are in any other setup where you're basically going to pay for extra data going to your compute resource, then HSDS can help. Because with HSDS, I don't think that have a case where there's 95% of the actual file went to my compute resource. HSDS is essentially would have slashed and just send me those bytes for the things that I was really needing.
Okay. Because when you upload a file in HSDS, doesn't it creates its own object store version of the file, doesn't it? Is that so? That's not
It
what you're
can.
doing here.
No, I just moved the file, just upload it to S3. There was no HDS involved. So yes, HDS can do that for you. Or it can work from the already existing HDF5 file and get the essentially do the same kind of reading like now here. Going to the file, reading the pieces it needs, and then doing its own thing. But what I want to say, but what? Yes, so that's, I hope that I don't have a nice drawing to explain this, but as I said, if you're in the cloud and you just want the simplest setup, and this is what I was interested in, because a lot of usage is kind of like this, and I wanted to see where HDF5 library stacks up, and especially the impact of cloud optimized HDF5 file. Because yes, HSDS can take the file. Now, if you tell to HSDS to actually turn it into its own storage format, then that version of your file will be cloud optimized. Yes. In this case, I was only looking at the files as they are generated, and then if that file can be cloud optimized before anything else. In other words, without or with HSDS involvement. Does that answer your question or clarify?
Yeah, no, sure. I've never used the S3 driver. Is it available through H5Py routinely? Is it just a matter of defining the?
Easy to tell. It depends where you get H5Py.
Okay.
If you install H5Py for PyPy, it's not going to be available. If you install H5Py from Conda Forge, then it will be available.
Okay.
So that's the difference, because the people who create H5Py binary packages on PyPy, they don't want to have extra external dependencies like curl, because the library needs to use libcurl to make HTTP requests and other things, and so they didn't want to deal with that. So PyPy version of H5Py doesn't have this S3 driver enabled.
Okay, but otherwise the core signatures from H5Py are identical once you
Yes.
mounted the file.
Yes, but if you get it from Conda Forge, you install H5Py from there. I know, because the HDF5 version in Conda Forge, the people who maintain that package there, they build it with the ROS3, this read-only S3 driver enabled as well. That's why. But the H5Py is its own, yes. I happen to have this maybe here. Let me see. There we go. So you see here how I'm basically saying open with driver, ROS3, and everything else. And then I have other parameters that I'm using to store it. And so that's all H5Py readily available.
Okay. So the critical thing is that page buff size, isn't it? That's what you say.
Yes. And the idea here is that you kind of, right now, there is no really good way, there is no way at all for the library itself to sort of on file open adjust itself to some kind of a smarter performance. The library is still very much defensive kind of programming. You need to tell it everything. And so it may change in the future, but right now that is, so I kind of assumed in the case of 16 MB, I wanted 128 MB page buffer. And in the case of 8 MB, I wanted 64 MB page buffer. So I wanted 8 file pages to be cached at any one time. And on top of that, this part here tells that every HDF5 dataset that is opened will have a chunk cache of 16 MB. And why I chose 16 MB? Because in one of these statistics that I conveniently jumped over, because it's too much to talk about that as well. Here, this one, the stable here. it told me that essentially if I choose 16 megabyte chunk cache, I will have all data sets in the chunk cache eventually if I need to. So I just didn't want to play games with chunk cache. You know, something is in, something is not in, whatever. I said, just load it up. I said, you know, today's computers, what's 16 megabytes here or there? Nothing. And so, of course, if you have bazillion data sets open at any one time, then, you know, and each one with 16 megabyte chunk cache, that's probably going to be the case. But I don't know if that's really a workable use case, really a likely use case.
That's very interesting. One final question then. Is the S3 driver, is that generic to all object stores, or is it specific to Amazon S3?
It is, well, it's specific to any object store that talks S3 API.
Okay.
To be honest with you, I have not tried it myself. I heard from some other people, very few, that they use it on Google, I think, and it tend to work. I'm not sure about Microsoft Azure. I don't venture there.
Okay, no, thank you. That's interesting.
So, yeah, so that's all.
Aleksandar.
Yes.
I had one question. If you just by default decide that you're going to design your HDF5 file to be cloud optimized because there's really no penalty for it, does that impose any additional burdens on your development process, or does it add any overhead? Does it make it harder? In other words, is it more expedient just to say I'm going to worry about the cloud optimization part later, or is that just kind of a best practice that you would say if you're starting from scratch, design it for cloud optimized?
I guess depends on what the performance, desirable performance. The only example I have is there is a NASA satellite mission that I'm collaborating with them now, and they decided to for the next release of their data, they want to produce cloud optimized files from the get-go, and they're not what I would say obsessed with performance. But they haven't seen any traceable impact on their ability to generate these cloud optimized files.
Okay, and then if you were doing A/B comparisons, did I understand you correct on the egress costs of S3? Will those add up?
Depending on the overall cost. I mean, relatively speaking, paying for data that leaves the cloud is a bigger cost compared to other costs. Now, if you have a lot of resources and then the amount of data gets out of the cloud is fairly small to compare to total cost, then obviously not. If you were looking at, I didn't count the cost. I didn't do the dollar math on, for example, how much would cost just running the instance in the cloud here, or how much would that cost to go out. I didn't do it. So I don't know. Generally speaking, again, as a general recommendation is if you are outside of the cloud, but your computation and data is in the cloud or any other services are in the cloud, then you definitely want to send only the most requested bytes outside of the cloud. That's the general approach.
Okay.
And the only way you can do it, especially, is if you have something like HSDS that's much more intelligent and aware of all these things. And so it's going to send you mostly the bytes that you really need. With a library, it's much more generic, basic type of data I/O. So it reads a lot of stuff, and then inside of its memory, which is in this case could be outside of the cloud, decides, oh, of all these bytes that I actually got, these are the bytes that actually I'm pushing forward to the application, and then that's what HSDS basically does for you.
Yes. Okay. Thank you.
All right. Anything else? All right. If not, I'm done. Thank you very much. Thanks for the questions. I was worried, will there be any questions or not? So it's always good to have some questions. And for me, this is the last, I think, for the year. Next month, I'm at a conference, so I'll miss my favorite, usual spot. So wish you Happy New Year, happy holidays, and then see you in January.
Great. Thank you, Alexander. Thanks, everyone. Bye.